Good morning, I'm Timothy Purcell, and I want to continue working with the Simplex method and linear programming. Here we're using the Simplex method to solve a standard maximum problem. And we left off in the previous video where I'd set up the Simplex tableau from the system of equations. But notice something, what you're going to want to do is you're not going to want to have to rewrite that, write that system of equations every time. You should see a pattern for how this matrix is made up. Look at what we did. The coefficients of x1, 1, 2, on the objective function we moved that term over so it became a -3. 1, 2, -3. 2, 2, move that term over, so a -2. 3, 1, move that term over, it became a -1. And then each inequality involving less than or equal to had a slack variable, slack 1 and slack 2. Slack 1 went into the first row, no slack 1s anywhere else. Slack 2 went into the second inequality, no S2s anywhere else. And now the last one, Z, all those terms were moved over, so you just had a -3x1 minus 2x2 minus x3 plus Z. So we have one Z, none anywhere else. Notice the slack variable columns and the Z column are going to have ones falling down there when you set it up and zeros everywhere else. On the right side of that vertical bar, 15, 10. You've moved all these terms over, so the only thing that's remaining on the right-hand side is 0. You'll always start off at 0 in the initial simplex matrix. So, to get started with the process, we ask ourselves, which one x value, which one decision variable has the biggest impact on the value of z if you could only increase one of them? Well, x1 has the biggest impact because it's being multiplied by 3. Whereas x2 is only multiplied by 2, x3 is only multiplied by 1. So the one that has the biggest impact on z, we're trying to get the biggest value of z possible, so we're going to use the column involving x1. Looking down here, those numbers are called my indicators. The biggest positive number in the objective coefficient in the objective function, when it was moved over, it became the most negative indicator. So you're going to have to select, by most negative, I mean the negative number with the largest absolute value. So select most negative indicator. That gives me my pivot column. X1 is going to be my pivot column. Now we have to determine what's called the pivot row. To do that, you take the number in the column of constants, divide it by the corresponding x1 value. You get 15 divided by 1, which is 15, and 10 divided by 2, which is 5. Now you want to make you're trying to make x1 as big as you can. You're trying to get z as big as you can, so you want to increase x1 as much as possible, but you can't just decide I'm going to raise x1 up to 1,000. If you chose something like that, remember you're operating under the restrictions of these inequalities. If you tried to use a 1,000 for x1, 1,000 plus non-negative plus non-negative, is that less than 15? Certainly not. The biggest x1 can be and have those inequalities still be true is 5. For the quotient, you choose the smallest positive. Now, if neither of those quotients is positive, then there's no maximum. There's nothing that says a maximum exists, okay? But for a standard maximum problem, there should be a maximum value. The reason we chose 5, if we use 5, 5 is less than or equal to 15. 2 times 5 is less than or equal to 10. If you tried to use 15, 2 times 15, is that less than 10? No. If you try to raise x1 up to 15, you're going to get an x value. You're going to get you'd have an x value that doesn't satisfy the inequality. So, once you've determined your pivot row, the number that's common to the pivot row and the pivot column, this is the pivot row. The number common to the pivot row and pivot column is called the pivot. So 2 is the pivot. 2 is the pivot. We're going to change that 2 to a 1. Remember how you perform those elementary row operations when using Gauss-Jordan elimination. That's why I stress that pattern. You multiply or divide to get a 1. You use that 1 to zero out the column. Then you go, that was the pattern we'd repeat over and over. So we have to change that 2 to a 1. The only way we can do it is by dividing or multiplying by 1/2. So we'll say row 2 divided by 2 gives me a new row 2. So row 1 and row 3 are not changing now. There's going to be a lot of recopying. People will try to get around all the recopying just by changing the rows, and invariably the matrix gets so messy that they mess up. So I find it's best just to put up with the recopying over and over. So divide by 2, that gives me a 1. Divide by 2, that gives me a 1. Divide by 2, that's a 1/2. Divide by 2, 0 divided by 2 stays a 0. 1 divided by 2 gives me a 1/2. 0 divided by 2 gives me a 0. 10 divided by 2 gives me a 5. Now, we have that pivot. Here's our pivot. Once you get your pivot changed to a 1, you use that 1 to zero out the column. And this process of zeroing out the column is called pivoting. So we're now pivoting around the pivot element of 1. Pivoting is the same thing as what we called zeroing out the column when we were doing the Gauss-Jordan elimination. Using this 1, you ask yourself, what does this number need to be so when you add it up here it gives you a 0? Well, it needs to be a -1. So we'll say -1 times row 2 plus row 1, not row 3, plus row 1 gives me a new row 1. What does this pivot need to be so when you add it to -3 you get a 0? You get a 3 times row 2 plus row 3 gives me a new row 3. Do y'all remember doing that, zeroing out the column? Whatever you wanted to change to 0, you'd multiply the pivot by the additive inverse, which means just change the sign. So row 2 is not changing now. Let me recopy it. Okay, so that's -1 plus 1 gives me a 0. -1 plus 2 gives me a 1. Multiply by -1, that becomes a -1/2 plus 6/2, that's a 5/2. Multiply by -1 and add it. Multiply by -1 and add it. Multiply by -1 and add it. Multiply by -1, that gives me a -5. Add it to 15 to give me a +10. Now the third row. Multiply by 3 and add it. Multiply by 3, that becomes a 3 plus a -2 is 1. Multiply by a 3, that gives me a 3/2 minus 2/2, that's a 1/2. Multiply by 3 and add it. Multiply by 3, that becomes a 3/2 and add it. multiply by a 3 and add it, multiply by 3, that gives me a 15, add it to give a 15. As long as you have a negative indicator on the last row, you have to continue the process. Those things are called indicators because they indicate whether you're through with the matrix reduction portion of the problem and are ready to interpret your solution. I look down here, that last row. There are no negative indicators, so that tells me I'm through with the. There are no negative numbers on the, oh, there could be negative numbers elsewhere, like there, but it's just that last row. You can't have negative numbers there. So now we're ready to interpret our solution. Remember how the columns were labeled: x1, x2, x3, s1, s2, and z. Let's convert the last row back to an equation. Converting the last row to an equation, we have 0x1 plus 1x2 plus 1/2 x3. We have 0s1, a positive 3/2 s2 plus 1z is equal to what? What number do we have right here? Yes, we have 15. Let's solve for z. Let's move all of these terms over to the right-hand side. That's going to give us z equals, we have a 15. We'll subtract x2, subtract 1/2 x3, and subtract 3/2 s2. Oh, no, I should have said something there. I'm sorry. I converted 0x1, 0x1, 1x2, 1/2 x3, 0s1, 3/2 s2 plus z equals 15. So I converted that last row to an equation, and then I solved that equation for z. I picked up those terms and moved them over to the left. So I had z by itself, and here's what I got. And now let's stop and think. This system of equations, we have 3 equations and 1, 2, 3, 4, 5, 6 variables. Remember when we were doing Gauss-Jordan elimination, I had said if you want a unique solution, you should be prepared to find the same number of equations as variables. Here, there are infinitely many solutions to this system. You have to find the solution that gives the largest value of z possible. Stop and think. What should we set x2, x3, and s2 equal to in order to maximize z? We have a z value of 15 minus. If we start assigning values to x2, x3, and s2, what do we need to assign to them so that we don't start shrinking down that 15? Remember, the x's have to be greater than or equal to 0. Also, the slight variables, just by the definition of less than or equal to, those slight variables are greater than or equal to 0. So what number should we assign? What number should we assign x2, x3, and s2 in order not to shrink down that 15? Could we assign it a 10? Well, if we do that, you're shrinking down 15. 0. That's what we should assign it. So x2, x3, and s2 are all going to be assigned the value of 0. The variables that are set equal to 0 are called non-basic variables. Generally, I just say they're the variables that are set equal to 0. I don't use that terminology that much. Now, come up here to the matrix that we just found. We're assigning x2 to 0. We're setting x2 to 0. We're setting x3 to 0. And we're setting s2 to 0. And once we do that, the remaining values, we can read off x1. Looking at the matrix, we go to the x1 column, and we go to the x1 column, we move down to the 1, we move across. That tells us that x1 is going to have to equal 5. Go to the S2 column. The S2 column, not S2, S1 column. The S1 column, move down to the 1, move across. We see that the slack 1 value is 10. And then the all-important z value. What's the biggest that z can ever be? Z, move down to the 1, can equal 15. So the maximum value of z is 15, and it occurs when x1 is 5, and x2 and x3 are both assigned the value of 0. I'm not going to want to do all of this stuff with the equations each time, okay? You need to be able to go from the matrix to your final answer. So I don't want to have to do, I want to be able to go from this matrix here, once we have no negative indicators, to the final answer. To do that, let's look at this matrix. You know something? Hold on. I'm gonna cover up everything. There's the final matrix, okay? There's the final matrix. There's the final matrix. I think it's easier to see the ones that are not going to be set to 0. Anything that has a single 1, all the rest 0, will not be set to 0. Their values to be read from the last column. A single 1, all the rest 0. A single 1, all the rest 0. Anything that has anything other than 1, 1, and the other zeros will be set to 0. So x2 is set to 0. x3 is set to 0, and S2 is set to 0. In the next example I do in the next video, I'm not going to write out this equation stuff here at the end. Once I have no negative indicators, I'll look which ones do I set to 0. It's obvious because they have all those numbers in the column. Which ones do I read from the last column? The ones that have all zeros and just a single 1. So anyway, I hope that's helped you with the simplex method, but now I'm going to do another video. I'm going to work out another problem, and we're going to go all the way through it, but we're going to skip over this equation stuff from the statement of the problem. We'll go straight to the matrix. We'll do the matrix reduction, the simplex process, and then we'll go from the simplex tableau with no negative indicators directly to the final answer. Okay, so let me find another example to do. Bye-bye.